Hi, this is Synthchaser from synthchaser.com. I've got a pair of Oberheim OB-X's here today that I'm going to be repairing. And before I get started on them, I realize it's been a while since I've done an Oberheim OB-X video, so I thought it would be a good opportunity to give you all a little tour around the inside of the Oberheim OB-X to get an idea of what makes it tick. This particular OB-X I got from another longtime tech who had gotten started on it, but very generously passed it along to me to finish up. This is a later model 6-voice OB-X, and good luck smiled down on me as I was able to get my hands on 2 additional original OB-X voice cards. This OB-X may not look the prettiest, but when it's done it's going to work and sound great. My understanding from the previous owner is that he rebuilt the power supply and repaired it so that it turns on, but it has some voice card issues. So I've already removed the 2 screws from each side, and I can lift the lid and we can get in. So over here on the left, behind this cardboard panel, is where our mains wiring enters the synthesizer. The power inlet, the switch, and the fuse are all located behind here. This other OB-X is missing the cardboard panel, and we can see the IEC inlet and the mains wiring back here. The mains wiring comes out here and goes to our power transformer, which in turn comes into the power supply board here on the left. There are some voltage regulators mounted on this heatsink on the left, and there are some connectors here that go to off-board voltage regulators that are mounted on large heat sinks on the back of the synthesizer. These are the heat sinks looking from the back of the synthesizer. Looks like the power supply has already been recapped with modern caps, with the exception of these 2 filter capacitors. And the bridge rectifiers, which are usually tucked away back here, have been upgraded and actually mounted onto the heatsink on the left. So other than confirming that it's working okay and that the battery here is still good, I probably won't have to do any work on this power supply, other than change these 2 filter capacitors. I show how to recap the power supply in a previous video, which hopefully I'll remember to link above right now. Next to the power supply, we have the processor board set here. This is a later OB-X, you can see it's running ROM revision J, and this has a slightly different processor board than is found on the earlier OB-X's. This is the earlier revision Oberheim OB-X, and while there's an aftermarket MIDI adapter installed, you can see that the upper processor board is much narrower than the one in the later revision. Also, there's no computer interface cable coming across the transformer to the left-hand side panel. So the way this board is logically divided is that the upper board has most of the digital logic. So we've got the processor, which is a Z80, like the other Oberheim OB series synthesizers. So there's the scratch pad RAM and the non-volatile RAM. Non-volatile RAM are the chips that are powered by the battery and save your patches when the synth is powered off. The OB-X uses these 6508 chips, which have 1024 addresses but only 1 data bit. There's only 4 of these chips in the synthesizer, not even 1 for each bit on the data bus. So this gives the OB-X a whopping ½ kilobyte of patch memory. This board also has the ROMs, which are these 3 chips here. And these are EEPROM chips, so they're erasable memory chips. And there's a little window on them under the stickers that you expose to ultraviolet light to erase the contents of the chip. So they put the label there, number 1, to block the window so that the data doesn't get degraded when it's exposed to ultraviolet light. And also to label the revision of the firmware code. So this is revision J, and this is chip 0, 1, and 2. These are 2708 ROM chips, the same ones that you find in earlier revision Prophet 5s, and they need 3 different power rails to work, plus 12 volts, plus 5 volts, and minus 5 volts. They still use these ROMs in the OB-SX and switched over to a single supply ROM with the OB-XA. Some of the address space decoding is done on the upper board and some on the lower board. Another thing on the upper board is a counter that's used in the auto-tune routine. So I mentioned this is a later revision board with the computer interface, so there's some additional chips here to implement the computer interface. And all these chips are tri-state buffers, which are buffering the address and data lines of this Z80 CPU. Because the Oberheim computer interface isn't really an interface, it's just a backdoor into this Z80 CPU. This simply provides direct memory access to the address and data bus of this CPU. A true interface wouldn't require you to know the memory map and internal implementation details of the host, and that's why you don't see a lot of products other than ones made by Oberheim that use this computer interface. So we can unscrew and raise this board to see the one underneath. This board has most of the common analog circuitry. So here's the DAC, which on this one is an AD7530 chip, and it's a 10-bit DAC. On the OB-XA they used a 12-bit DAC, and on the OB-8 they used a 14-bit DAC. The more bits on the DAC, the greater the resolution your parameters can have. So if you were to sweep your filter on an OB-X, there would be 2 to the 10th power, or 1024 steps in the filter CV as you turn from one end to the other. With a 12-bit DAC, there would be 4096 steps, and with a 14-bit DAC, over 16,000 steps. The advantage of more bits in the DAC is that with a higher resolution, your ears won't hear any stepping as you sweep through the values. For reference, the Oberheim 4-voice only had a 6-bit DAC, which had only 64 steps. So the OB-X was a big step up in that regard. We've also got a lot of sample and holds on this board. By sample and hold, I'm not talking about the sample and hold feature that you'll find on many synthesizers, but I'm talking about a specific type of circuit upon which that feature is based, but here is being used for a different purpose. You can think of these sample and holds as sort of an analog memory device. You'll see a lot of these banks of film capacitors and IC chips. These particular ones here are polystyrene capacitors, and the chips are op amps that are configured as straight buffers. When the CPU addresses one of these analog memories, the voltage on the output of the DAC will be routed through some demultiplexers, and these polystyrene or film capacitors will charge or discharge to that level. And that's the sampling part. The holding part entails keeping that capacitor charged to that same level through a combination of the low leakage of the capacitor dielectric and the high impedance buffer that follows. In this case, these capacitors are polystyrene, which have excellent low leakage characteristics, and the op amps used for a buffer are TL082, which is a JFET input op amp and has an incredibly high input impedance. So the result is the synthesizer can use one DAC and make a whole bunch of analog control voltages available at the same time to the voice boards. So the processor board is the central board in the synthesizer, and there's lots of different connectors on it that are running off to all the other boards. For example, the power supply comes in here. The bender assembly is connected here. This ribbon cable down here runs off to the key bed, and the key bed is a Pratt Reed key bed with the keys arranged in an 8x8 switch matrix. I have another video on how this key bed works and gets scanned. If you're interested, I'll hopefully remember to link it above now. All of these Molex connectors here on the right run off to the voice boards, which I'll get to in a minute. And then this ribbon cable here runs up to the circuit boards that are mounted to the front panel. So this is the back side of the boards mounted to the front panel. Basically, these boards hold the potentiometers. You can see the back side of the potentiometers here. The push button switches and LEDs are on these boards. And there's some IC chips with simple logic to scan the switches and drive the LEDs as matrices, and to multiplex all the pots so they can be scanned one at a time by the CPU. There's also this little red dip switch block here. This can be used to turn off one or more voices. The factory used this because they would ship units with 4, 6, or 8 voices, and they use this to configure their build. It's also helpful while servicing the synth, and sometimes I see people use it to turn off a malfunctioning or off-sounding voice so they can still use the synth until they get it fixed. And although this is a 6-voice OB-X, I see that only voices 1, 2, and 3 are turned on, so I'm going to suspect that there's something wrong with voices 4, 5, and 6. On the earlier revision OB-X, you can see that it doesn't have the dip switch block, but rather 5 slide switches. The 2 switches here on the left are the same test 1, test 2 switches that are on the later revision, and the 3 remaining slide switches are used to configure the number of voices that the synthesizer will address. There's 3 switches which represent an octal number, so there's 2 to the 3rd power, or 8 possible voices. You can't get this revision to skip over a voice, so if you wanted to remove a voice from rotation on an 8 voice, you'd need to configure these switches for 7 voices and then move the card you wanted to remove to slot number 8. Over here on the right side of the synthesizer we have the voice boards, these guys here. Each one of these circuit boards is basically a little analog synthesizer,
just without any user controls. Each voice has 2 VCOs, a VCF, 2 ADSR envelope generators, and a VCA. The control voltages in logic, like for gate and waveform selection, come from the processor board we looked at earlier, come across these Molex connectors onto these voice card motherboards, and then they're made available to the voice cards on these connectors here. So there's 2 trays, each with a motherboard that holds up to 4 voice cards. On the right side of the motherboard there's some trimmer pots, and they control the panning of the individual voices. This cable links the 2 motherboards, so if we disconnect it, we can lift this tray up, and we see another motherboard with 4 more voice cards on the bottom. They also have their own set of panning pots. On this lower motherboard there's some additional circuitry here on the right hand side, which serves as a final VCA stage controlled by the master volume knob. The final output comes here and goes up to the 1/4 inch jacks on the back of the synthesizer. So here's an OB-X voice card. As I mentioned before, each voice card has 2 VCOs. The VCOs were built mainly out of discrete transistors, which you can see in this area of the board. Underneath here there's a chip, which is a CA3086 transistor array, which had 5 pretty closely matched, for the time anyway, transistors, thermally coupled on a single die. Each of the VCOs used 2 of those transistors for its exponential converter, and you can see the Tempco resistors for the 2 oscillators touching this transistor array chip. The oscillator design was substantially the same as the oscillators in the Oberheim SEM. The OB-X has a 2-pole filter made out of cascaded OTAs, or operational transconductance amplifiers. So the 2 filter stages are over here on the right-hand side of the board. The OTA that was used was the CA3080. They also used a 3080 for the VCA, and that's this one here at the bottom. So the VCOs, the VCF, and the VCA so far are substantially the same as the SEM, and were made from discretes and very basic building block linear IC chips. Where the OB-X differed from the SEM was the envelopes. There are 2 ADSR envelopes, and instead of being built out of discrete transistors like on the SEM, Oberheim used these CEM3310 envelope generator IC chips. This was a small first step toward moving entirely to Curtis chip-based voices, like we see on the later synthesizers. Interestingly, some of you might remember not too long ago I repaired a newer Tom Oberheim SEM Pro on the channel, and we saw that the envelope design on the new SEM was also different from that of the original SEM. It didn't use Curtis chips, but rather CPU-controlled analog switches. So I guess the SEM envelopes were expendable way back then, and they're still expendable today. And one final note about the voice card, you'll notice that this one is slightly different from this one. Can you spot the difference? It's right here. The gate LED was added to later revision OB-X voice cards. So this particular OB-X has a mix of older and newer cards. So what are the weak links in the OB-X? What things do we proactively want to take care of because we know they're going to cause us grief? Or at least, bare minimum, keep a mindful eye on as we go. Starting over here on the power supply, the original bridge rectifiers were a bit wimpy and tend to fail, so I'll typically beef them up and at the same time recap the power supply. In this case, the power supply has already been recapped and looks like the bridge rectifiers have been replaced with these guys mounted to the heatsink. On this earlier revision OB-X, the power supply capacitors look original, including the tantalum ones down there, and the bridge rectifiers are those tiny little wimpy little guys down there, and they need to be replaced. I have a kit on my website with all the capacitors and the bridge rectifiers that you'd need to rebuild one of these power supplies. On the subject of capacitors, all throughout the synthesizer are tantalum capacitors, like these little blue blobs here. While in general tantalum capacitors behave well so long as you don't expose them to overvoltage, these particular tantalum capacitors that are found in the OB-X and some other vintage synthesizers from the same era, most notably ARP, are unreliable, have a high failure rate, and are prone to short out even when not exposed to overvoltage. Consequently, they all need to be replaced. From a prior video, here's what one looked like when it shorted out and exploded on an OB-X voice card. The tantalum capacitors are all over the synthesizer. They're on the power supply, though this power supply has already been recapped. They're on the processor board, they're on the pot boards, they're on the voice cards. This one has had some of them replaced, but not all. On the voice cards, besides the tantalum capacitors, another thing that's prone to go bad are the trimmer pots. These little guys here. There's 11 different trimmers on each of the voice cards, and each one is used to tune and calibrate some area of it, like the oscillators, the filter, or the VCA. So I'm sure you know how potentiometers get scratchy over time. Well, trimmers are just little pots, and they're not even sealed up as well. Besides getting dirty, I often find the wiper damages the carbon track around where it's been parked, because it's probably been sitting in that same spot for decades. Often when I go to adjust these trimmers, I'll find a dead zone around where it had been parked, resistance will jump around, or something like that will prevent me from using the trimmer to calibrate the synth. And when they put glue or paint, or in this case both, on the trimmer to fix it into position, you can pretty much guarantee that you're not going to be able to calibrate this with this trimmer. Sometimes I've not even touched the trimmer and I'll find that it's responsible for some voice card problem. Another beef I have with the trimmers is that their range is very broad. As a result, a small movement of the trimmer can make a big movement in the thing you're calibrating. For example, like the volts per octave scaling of your filter. And that makes it hard to get a really good calibration done with the original trimmers. So for years now I've been putting together voice card rebuild kits. These kits have replacements for all the polarized capacitors and trimmers on the voice cards, and it replaces all these single turn trimmers with multi-turn type trimmers. The trimmer footprints aren't the same as the original, so it's a little fiddly or cheesy to fit them in there, but in my opinion the results are worth it. On the topic of the voice cards, another high failure rate item is this dip switch block. I mentioned these switches earlier, but a common problem I have is when I turn off one of the voices, the switch doesn't work to turn it back on. So this block of switches needs to be replaced, and I include it in my voice board rebuild kit. Another area I commonly find problems in are the cables with the Molex connectors. In particular, this set of cables between the two pot boards on the panel and all these cables down here that connect the processor board to the voice boards are really problematic. I guess even Oberheim thought so too, because in the OB-XA, all of these cables were replaced with an IDC ribbon cable. And by mid-run of the OB-8, these cables linking the pot boards had been replaced with cables soldered directly to the boards. It actually looks like the motherboard cables here caused someone a problem at some point. Let me zoom in and show you how I can tell. So looking at this closely, we can see that someone soldered on the Molex contacts here and some on this one too. Let's hope they didn't solder those contacts to the headers themselves. But here's the thing. These Molex contacts are crimp contacts, not solder contacts. I see people on the internet giving bad advice about soldering them in addition to crimping them to make them, quote, more reliable, but that's really a big no-no. Without going into too much detail, there's a reason these cables are built with stranded wire instead of solid core wires, specifically to be flexible, because you're going to be flexing them when you plug and unplug them, and you don't want them to break. Well, when you solder the wire to the contact, the solder wicks up that stranded wire, and you've lost the whole benefit of the stranded wire. So I know the Molex connectors were giving someone problems, and I don't like the way it was fixed. So I'll be crimping new contacts to replace every single Molex connector in the synthesizer. Not just the ones that were soldered or the individual bad ones that I find when repairing the synth, but proactively to every contact in the synthesizer. Not all the cables come detached on both ends, but the worst offenders do. The pot board cables, the processor board to voice board cables, and then this cable here that links the two voice motherboards. For those, I have replacement cable sets on my website for those who aren't crimp masters. I use an upgraded type of Molex contact that instead of contacting the header pins on one point like the old contact does, makes contact on 3 sides for a more reliable connection than the original. Finally, another area that we're pretty much guaranteed to find some amount of problems with are the CMOS chips. There's a mixture of TTL and CMOS logic chips in the OB-X, but it's pretty heavy on the CMOS. And they used a lot of CMOS chips manufactured by RCA, which are really failure prone. And you can see they're down here. You You can identify them because they have the company marking RCA on them, on the processor board, on the voice cards. And it seems the older the RCA chip, the higher the failure rate. I don't advocate going around and shotgun replacing all the CMOS chips in these synthesizers. It's just something to keep in mind when working on the synthesizer. As I go through the process of getting the synthesizer fully working and calibrated, it'll become obvious to me if there's any bad chips. And the synth will have tons of burn-in time to make sure that the chips are good and not just on their last legs.
So there we have it. We looked inside a couple different Oberheim OB-X's. We talked about what makes them tick, differences between revisions, and we looked at some of the things that you'd want to keep an eye out for when working on one of these. If I come across any interesting problems when working on either of these two, maybe I'll make another video. My name is Synthchaser from synthchaser.com. Thanks for watching and have a great day.